The next topic is types of semiconductor. The types of semiconductor. Semiconductors can be broadly classified into two categories. One is intrinsic semiconductor and the other one is extrinsic semiconductor. One is intrinsic semiconductor and the other one is extrinsic semiconductor. A semiconductor, I'll tell you first about intrinsic semiconductor. A semiconductor is a extremely purest form is known as an intrinsic semiconductor. A semiconductor is in a extremely pure form. A semiconductor in extremely purest form. Purest form should be present in extrinsic semiconductor. This type of semiconductor is called as intrinsic semiconductor. For example, pure silicon and germanium. Pure silicon and germanium are the examples for intrinsic semiconductor. In intrinsic semiconductor, the number of free electrons is equal to the number of holes. Number of free electrons is equal to the number of holes here. And number of NH, Ne is equal to NH is equal to Ni here. So what is Ni? Ni is intrinsic carrier concentration. Intrinsic carrier concentration. So number of Ne is equal to NH is equal to Ni. So number of holes is equal, number of electrons is equal to the number of holes, which is equal to intrinsic carrier concentration. The next topic is expression for total current in an intrinsic semiconductor. So here in intrinsic semiconductor, free electrons move completely independently as conduction electrons and give rise to an electron current IE. So under an applied electric field, because in the presence of electric field, so IE is produced here. Remember that the motion of hole is only a convenient way of describing the actual motion of bound electrons. Remember this. Whenever there is an empty bond anywhere in the crystal, under the action of an electric field, these holes moves towards the negative potential, giving the whole current, which is IH. Okay. So the total current I is equal to the sum of electron current IE plus the whole current IH. So the total current I is equal to IE plus IH. So electron current and whole current here. So the total current is thus the sum of electron current and the whole current here. So it may be noted that apart from the process of generation of conduction of electrons and holes, a simultaneous process of recombination occurs in which the electrons recombine with holes here. So I'll repeat again. The recombination in which the electrons recombine with holes here. So the electrons will recombine with holes. The recombination occurs due to an electron colliding with the hole. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. I'll repeat again. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. The next topic is intrinsic semiconductor with variation of temperature with energy band diagram. So intrinsic semiconductor with variation of temperature with energy band diagram. So an intrinsic semiconductor will behave like an insulator at temperature 0 Kelvin. So an intrinsic semiconductor will behave like an insulator at 0 Kelvin. So as shown in this figure, it behaves like an insulator here. So it is the thermal energy at higher temperature, that is the temperature greater than 0 Kelvin. Okay, the temperature greater than 0 Kelvin which excites some electrons from the valence band to the conduction band, which will excite some electrons from valence band to the conduction band, valence band to the conduction band. These thermally excited electrons at the temperature greater than 0 Kelvin, temperature greater than 0 Kelvin, not the temperature equal to 0 degree, 0 Kelvin, but the temperature greater than 0 Kelvin partially occupy conduction band. So it will occupy the conduction band as shown in this figure here. Okay, you see the electrons have come from here to here and they are placed here. Okay, so therefore the energy band diagram for the intrinsic semiconductor is shown here. Okay, here some electrons shown in the conduction band, these will have come from the valence band, leaving equal number of holes there. So here the electrons have come from valence band to the conduction band, leaving empty spaces or empty holes here, because the electrons that they were present here have moved from here to here, leaving empty spaces here, which are called as holes here. So equal number of electrons which have gone here have found equal number of holes in the valence band here. Let us know about few terms here. The first one is doping. The process of adding impurities to pure semiconductor is called as doping. I'll repeat again. The process of adding impurity to pure semiconductor is called as doping. Then what do you mean by dopant? The impurity added to pure semiconductor is called as dopant. The impurity added to pure semiconductor is called as dopant. So there are two types of dopants used in doping the tetravalent silicon or germanium. So there are two types of dopants here. So one is tetravalent impurity and next one is trivalent impurity. The examples for pentavalent impurity are phosphorus, antimony, arsenic, etc. And the examples for trivalent impurities are aluminium, boron, indium, gallium, etc. The next topic is extrinsic semiconductor. The doped semiconductor is called as extrinsic semiconductor. The doped semiconductor is called as extrinsic semiconductors. So depending upon the type of impurity added, extrinsic semiconductors can be broadly classified into two categories. One is N-type semiconductor and the other one is P-type semiconductor. First, we shall know something about N-type semiconductor. Okay, so the N-type semiconductor is obtained when a pentavalent impurity is added to pure semiconductor. The pentavalent impurity like phosphorus, we have taken phosphorus here. It is a pentavalent impurity. So 1, 2, 3, 4, 5. 5 electrons will be there. Okay, 5 valence electrons will be here. So the pentavalent impurity like phosphorus has 5 valence electrons. So we have taken the phosphorus here. Okay, then 4 of them form covalent bonds with 4 neighboring atoms, leaving a free electron. So here 1, 2, 3, 4, 4 electrons have formed covalent bonds with the neighboring atoms, but there is one atom which seems to be left out from here. Okay, so thus every pentavalent impurity atom donates one free electron for conduction. So there will be one electron left for conduction here, as you can clearly see here. So the pentavalent impurity atom is called donor impurity. So it is called as donor impurity. The free electrons donated by donor impurity are available for conduction even at 0 Kelvin. Even at 0 Kelvin. You have to know this. Okay. So in N-type, number of free electrons are greater than number of holes. Number of free electrons are greater than number of holes. Hence, majority charge carriers are free electrons and minority charge carriers are holes here. I'll repeat again. The majority charge carriers are free electrons and minority charge carriers are holes here. So Ne is very much greater than NH. So number of electrons is greater than number of holes here. The next topic is P-type semiconductor. Like N-type, even this is one more type, an extrinsic semiconductor. The P-type semiconductor is obtained when a trivalent impurity is added to pure semiconductor. There we have used pentavalent impurity in N-type. Here we will be using trivalent impurity in P-type here. The trivalent impurity like aluminium or boron will have 3 valence electrons. Only there will be 3 valence electrons. 1, 2, 3. So 1 there will be hole here. So 3 valence electrons will be present in trivalent impurity. The trivalent impurity like aluminium or boron, I have taken boron here. So the 3 valence electrons form covalent bonds with the neighboring atoms, leaving a hole here. Here the 3 valence electrons have formed covalent bonds with the neighboring atoms, forming a hole here. So they have left out a hole here, forming 3 covalent bonds with the neighboring atoms from the valence electrons here. Thus, every trivalent impurity atom donates 1 hole for conduction. So the trivalent impurity atom donates 1 hole for conduction. Hence, trivalent impurity atom is called acceptor impurity. There goes donor impurity. Here it is an acceptor impurity here. It is called as acceptor impurity. The hole created by acceptor impurity are available for the conduction even at 0 Kelvin. Even at 0 Kelvin, like that. Even at 0 Kelvin. So in P-type, in P-type, number of holes is greater than number of free electrons. I'll repeat again. In P-type, number of holes are greater than number of free electrons. Therefore, majority charge carriers are holes and minority charge carriers are free electrons. I'll repeat again. The majority charge carriers are holes and minority charge carriers are free electrons. So, number of holes is always greater than number of electrons here. The next topic is N-type semiconductor on the basis of energy band diagram. So we are describing N-type semiconductor on the basis of energy band diagram. Okay. In this N-type semiconductor, the energy band diagram of N-type silicon semiconductor, the donor energy level ED is slightly below the bottom EC of the conduction band, and the electrons from this level move into the conduction band with very small supply of energy. So you can clearly see that ED is here and EV is here and EC is here. I'll repeat again. So the donor energy level ED is slightly below the bottom EC. So the donor level ED is slightly below the EC here. Okay, or that is of the conduction band, and the electrons from this level move into the conduction band with very small supply of energy. So that is very small supply of energy. At room temperature, most of the donor atoms get ionized. Most of the donor atoms will get ionized, and very few atoms of silicon get ionized here. Very few atoms of silicon get ionized. So the conduction band will have most electrons coming from the donor impurities. So the conduction band will have most electrons coming from the donor impurity as shown in this figure. The next one is P-type semiconductor on the basis of energy band diagram. So this is the energy band diagram of the P-type semiconductor. In the energy band diagram of the P-type semiconductor, the acceptor energy level EA, is here. It is slightly above the top EV. It is slightly above the top EV of the valence band as shown in this figure. So you can clearly see that EA, EV, EC, they are all here. This is the energy gap here. With very small supply of energy, an electron from the valence band can jump to the level EA and ionize the acceptor negatively. So I'll repeat again. With very small supply of energy, an electron from the valence band, can jump to the level EA, from here to here, can jump to the level EA and ionize the acceptor negatively. That is, a hole from the level EA sinks down into the valence band. A hole from the level EA sinks down into the valence band. Electrons rise up and holes fall down when they gain external energy. I'll repeat again. Electrons rise up. Electrons will rise up. Okay. Then the holes will sink down. That means the holes will come down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. I'll repeat again. At room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. The density of holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. I'll repeat again. The density of holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. The electron and hole concentration in the semiconductor in thermal equilibrium is given by NH is equal to Ni square. NH is equal to Ni square.